So, good evening, everyone, and welcome to all the course coordinators, course participants. So, today we have a lecture on the satellite based augmentation system, wherein we will discuss the GPS aided geo augmentation navigation, that is GAGAN, also for the Indian region and the neighboring region. So, now we are dealing with a multi constellation, multi frequency GNSS environment, which has become very clear from the previous lectures. So today's outline will cover the revision part. Then we will discuss the augmentation systems, why we are using these augmentation systems, what are the various augmentation systems like VAS, EGNOS, GAGAN, and what are the positional accuracies expected from these kind of systems, GNSS and these kind of systems, and the course we have already covered basically, and then the various aviation applications. So as a part of the revision, I would like to cover again that by now we have very clearly understood that the satellite based navigation system provides us the latitude longitude of any place where the receiver is there, along with the elevation of that receiver with reference to the datum selected. Okay, so usually we are selecting the WJ34 datum, which is the best fit curve to the earth where we are referring to. However, we can change to other datums also using the conversion parameters, and this has been automated in the softwares which we are using for the GPS. Besides the position, we are also getting the velocity. Okay, and we are also receiving the time, and these things we are getting in a common reference frame. So we can use the same receiver anywhere in the globe, irrespective of the country or the local systems. The GPS is going to work with respect to the WJ34 datum in the Earth-centric Earth fixed coordinate system. Day or night, good or bad weather, whatever it is, it will provide us the position, velocity, and timing in a common reference frame. That is the advantage which we have with the satellite-based navigation system. Further, we have also discussed that the ICAO has given a wider spectrum definition for the GNSS, wherein it has combined all the satellite constellations, that is the GPS, GLONASS, Galileo, Beidou, IIRS, QZSS, along with the aircraft receivers and the system integrity monitoring systems working on the ground stations or otherwise too. They can be on the some mobile platform also, and these are augmented or processed as necessary to support the required navigation performance for the intended operation. So depending upon the application, it should be able to provide the required accuracy either via the direct satellite connectivity or through the internet based services or through the GSM or the SIM card based services. All these modes of data transmission or the transmission of correction parameters or the final derived outputs, all of these are feasible nowadays because of the development in the technology. Then we have seen that the positional accuracy what we receive is of the order of 10 to 20 meters, whereas the velocity is of the order of the 10 centimeter per second for various systems. The timing accuracy varies for various systems from 15 nanosecond for Navistar GPS to 20 nanosecond for GLONASS, Galileo, Beidou 1, 2, and 15 nanosecond for the global Beidou, and 15 nanosecond for the IIRS also. So that we have discussed yesterday, and they are referring to the different ellipsoids also. However, these conversions are taken care by the software because of the collaborations which are taking place. And then we have understood that the GPS is a 6 orbit based system where it's a dynamic system. Earth is moving along with the satellites in their orbits, and the visibility of satellites at any point of time over any location of the earth is also changing. We can see that this number is changing because of the dynamicity of the system. Then we have also covered the basic part of the signals along with the other additions also. So in this slide I have shown the basic one only, where in L1, L2 carrier waves are used along with the CA code and the P code. However, we have discussed the L5 frequency, L1C, L2C and M code also in the previous lecture. Then we also discussed that we are using the satellite laser ranging, GNSS, very long baseline interferometry, DORIS, SAR interferometry and altimetry also for various space-based geodetic solutions for the requirement of the generation of the topography of the earth or position of a point over the earth, or for computing the deformations taking place on the surface of the earth. So in SAR interferometry and altimetry, they will be covered particularly in different lectures during the application session also by various speakers in the module on the application. Then we discussed about the two open source books also, GPS, the first GNSS by the Trimble, it's the open ebook, and an introduction to the GNSS, a third edition by the Novatel. So these you can refer. You can also take the PDFs of the lecture covered in this series through the material box, wherein the EduSet team is keeping the material for you. Then we also discussed the single frequency, dual frequency and multi-frequency receivers. So we covered that single frequency receivers are good for baselines up to 15 km, whereas the dual frequency receivers can be used for longer baselines along with the scientific softwares for more or improved processing. Then the various classes of GPS receivers also discussed. The geodetic class providing us the sub-centimeter level accuracy, mapping grid receivers providing us an accuracy of the order of 3 meters or so, whereas navigation based receivers, they can provide an accuracy of the order of 10 meters. Thereafter we have talked about the error budgets also that are there with the satellite clocks, orbital errors, ionospheric errors, tropospheric errors, receiver noise and multipath basically, and what among these can be improved with the help of the differential GPS. So these things we have covered in the previous lectures along with the different methods of the surveys, static method, then the rapid static method, stop and go survey and kinematic survey. So for the longer baseline we go for a long duration of observations at the base station and the rover stations, so that we have common satellites minimum 4 between the base station and the rover station. The method for the correction was also discussed for the GNSS using the known values x, y, z of the base station and the x prime, y prime, z prime values for the position of the base station through the broadcast ephemeris data. Okay. So this error components delta x, delta y, delta z are computed at the base station and are used for the corrections at the rover station. So that's the way we have been moving from the last week till yesterday. Now today we will cover the satellite based augmentation system. So the International Civil Aviation Organization has developed the standards and procedures for supporting the transition to the communication, navigation surveillance and the air traffic management. Basically the ICAO has the responsibility for preparation of the SOPs for safe flying of the aircrafts across the globe. So that is how they come into the picture, as they have a larger responsibility and they have defined the GNSS as we have discussed in the previous slides. So they have made a very large definition constituting all the constellations, aircraft receivers and the system integrity monitoring systems on the ground. So primarily what is happening, that all the systems which are working besides the standalone, they are using the DGPS in the processing at the back end, whether it is precise point positioning or RTK GPS. In the background all the processing is based on the DGPS principle. So the SBAS systems provides wide area or regional augmentation through the use of additional satellite broadcast messages, which are done through the geostationary satellites. So corrections are computed at the ground stations where we already know the coordinates accurately. They are the surveyed stations, and the errors are computed at those stations, and these errors as a measure of the correction parameters are sent to the geostationary satellites, which are used for providing the corrected coordinates to the user. I'll just explain it again through this diagram that this is the master control stations, which is getting the information from the reference stations where we have round the clock working GNSS receivers. The coordinates of these reference stations are known, and in real time the coordinate of these reference stations are computed as well from the signals arriving at that station in real time. So that means through the broadcast ephemeris. So we have a known value xyz for this reference station, and we compute a x prime, y prime, z prime coordinate for this as well from the real time broadcast ephemeris data. Okay, now this two values, the known value of the reference station and the computed value of the reference station, provides us the errors at that moment in the xyz. Now these errors are used for the correction parameters, and then these parameters are sent through the uplink station to the geostationary satellite, and the geostationary satellite again send the corrections to the users on the ground. So we have a performance based navigation manual also for this, which can be referred. Now this geostationary satellite has a major role to play here because it received the correction parameters from the ground master control station, and it repeatedly broadcasts the correction parameters for the regular use by the users. Now various satellite based augmentation systems are available, such as wide area augmentation system for the US, GAGAN for India, then EGNOS for the European region, AMSAS for Japan, then and the QZSS quasi satellite system, that is the regional navigation satellite system for Japan, SDCM for Russia, EGNOS for China, and this for the Caribbean islands, SCCSA, that is for the Caribbean islands. And these are used along with the other techniques also, the national level DGPS developed by the US, CORS stations, GDGPS, and the IGS stations also, which are also available for various applications. However, the topic of today's concern is the SBAS. Now we are getting different solutions from all of them, and we are computing a single solution. Okay, we have GPS, GLONASS, Beidou, Galileo, IIRS, QZSS satellites working in different datums and finally providing a single value. So that is what is being referred here as the integrity. That when we are finally computing, is it trustworthy? Will that be the correct solution what is being provided by that? So the ultimate thing is over the integrity of the solution. So for that we have integrity management system, that when we combine all these various systems under the GNSS umbrella along with the application of the SBAS computations, we should get the correct solution. So this is how the different VAS systems are available in the US, in the CVAS in the Canada, EGNOS, GAGAN, AMSAS, SDCM, and then some systems are working for Australia, African region also. These are being prepared and applicable for the South American region also. So different systems are being developed, and we can see these on the websites also as they are being maintained. The datasets are available over the websites. The links are also provided in the slide. The PDF of the slide will be made available to you, and the system is working quite transparently, and you will get all the data for the use. So the long-term 2020 and 2025 plan shows that the entire globe is covered with a network of SBAS systems. Okay, because these are different systems: Canadian VAS, AMSAS, GAGAN, ESNAS, EGNOS, and SDCM for Russia. So like that, for over the entire globe, we have different systems which are being placed. This is shown in this figure as well. Okay, SDCM for Russia is shown here. So entire Earth is being covered by this system. The usage, however, definitely depends upon the adaptability of the users that they actually use it. Now, why we are using the SBAS? Because it provides correction to the GNSS solution in real time, which is needed for the industries which need real time high accuracy values, such as the aircraft industry. So for the landing and takeoff of aircrafts and the en route navigation of the aircrafts, we need improved values. So we have receiver automated integrity monitoring system for the aircraft based augmentation system, and this provides a higher accuracy for the area navigation. Now, the earlier case, what was happening, that we have the very high frequency omnidirectional range antennas on the ground, distance measuring devices or the equipments, DMEs are there, which are being followed by the aircrafts. So in that case, what happens, that aircrafts basically, when they go from point A to B, let us say from Dehradun to Hyderabad, they can fly in a direct path from Dehradun to Hyderabad. However, they cannot do that because they have to be connected with the DMEs or the VORs on the ground, and their distribution is not uniform all over. So they follow a zigzag path. You might have noted that instead of following a point to point direction, they follow a zigzag path. So, but if we are using the SBAS system, then in that case, the direct movement is possible. So this direct movement will save our time, and the improved values of the coordinates will provide more improved availability of the area for different aircrafts, because nowadays in airspace also we have a lot of congestion because of large number of flights which are moving. So they can have a better management. You can say that the traffic density can be increased with the more improved coordinates for the aircrafts, because the safety concern has to be there, and if we have better coordinates, better 2 sigma values, then we can fit more aircrafts in a lesser space. So that management can be improved. Then in the US, actually they have about 4,000 around aircrafts, airports, and out of these 4,000 airports, about 1,100 airports do not have the integrated landing systems, and they are using very successfully the VAS system for the landing and takeoff. So that is a perfect practical example of usage of the SBAS for the aircraft industry. That there are airports which are 1,000 plus in numbers, and over them we are using the VAS for the landing takeoff operations. What does it mean actually? It means that there is a high amount of reliability of the satellite based augmentation systems. Same should be done throughout the globe also, with the many benefits which it has, and we will be discussing in the coming slides. Then we have the local area augmentation system also, and definitely this is a cornerstone for the national airspace system in the US, because large number of airports are totally dependent on VAS because they do not have integrated landing system. They are the non-ILS airports. Okay, and even in the emergency landing cases, VAS kind of services or the SBAS kind of services can be more helpful because small spaces can be used more efficiently with the improved accuracy of the coordinates what we are getting from the SBAS. Even shorter runways can be utilized more efficiently. In that case, the chances of overshooting a runway is less because the touchdown can be done prior to the point where do otherwise. That is, in the case they do not have VAS, they have to take more precaution, and thus they have to leave more space for safety purpose. But when we are using the VAS, we have a more efficient use of the airstrip also. So basically, the SBAS system or GBAS systems, they help the aircrafts in the movement throughout during the takeoff, departure, cruise, metering, descent, final approach, and landing. All the stages they are benefited by the SBAS, and you can see that in that case we need not to follow a zigzag path. We can follow a direct route from the origin to the destination. This will provide enhanced safety, increased capacity, it will reduce the delays, and it will have increased flight efficiencies. The predictability of the aircraft landing and takeoff will be better, that schedule can be followed in a better way. And since in the direct route the consumption of fuel is less, so this method is more environmental friendly also. So we can see if we are applying the SBAS system, we can achieve accuracy of the order of better than a meter in case of the wide area augmentation system that is used in the US. So their performance is, if they are doing it standalone mode, they are getting accuracy of the level of about 3 meters in horizontal, 4 meters in vertical, which improves to better than a meter for the horizontal and 1.2 meter for the vertical. So that is the advantage with the usage of the satellite based augmentation system. This particular table refers to the wide area augmentation system which is used in the US. So design is same as we have discussed. We have master control station and the reference stations on the ground. The data received from the reference stations is corrected, and correction parameters are sent from the uplink station to the communication satellite, that is the geostationary satellite, using C-band data, and this is transmitted to the user on the ground or the aircraft or in the ocean, because it is not restricted for one industry only. Anybody who is having a adequate receiver can use it. So the Federal Aviation Administration and the Department of Transport has developed the VAS system for US for precision flight approaches. It provides more accuracy, improved integrity, and the availability of the correction parameters, because one of the advantage by involvement of the geostationary satellite is that the correction parameter can be sent to a larger footprint on the ground. VAS corrects for the GPS signal errors caused by the ionospheric disturbances, timing, and satellite orbit errors, and it provides vital integrity information regarding the health of each satellite. So all this is being taken care in the satellite based augmentation system. Although we are talking about the VAS here, but the SBAS system which are there all over the world, established by different countries, they work on the same principle. So it is providing support in the en route arrival and departure. It provides increased availability of the GNSS corrected signals because of the involvement of the geostationary satellites. It provides enhanced safety using the vertical guidance. In case of no ground hardware, as I have told, that non-ILS stations also use uh, VAS system in US. About 1179 airports are working only on the VAS system. So finally, it is providing a good example for the globe wherein VAS is used for the aircraft industry. Then we come to the local area augmentation system or the ground based augmentation system. So in this case, what happens, we have very high frequency data broadcast antennas over the airports, and it is possible that uh, of course we have the geostationary satellites, but these antennas can directly transmit the corrections to the aircrafts. Okay, so that is why we are calling it a local area augmentation system or the ground based GBAS. So that is also possible. So it will provide the real time corrections or the differential corrections to the pilot, which will be utilized for the purpose of the takeoff, landing, or the en route operations. Here we have to understand that the nearer we are to the reference station, the more correct values we are going to get. As we are moving from the away from the reference stations, we have some decreased accuracy, but the best accuracy we will get near to the reference stations, and we have seen that up to 15-kilometer baselines we have no issue. So normally in takeoff and landing there is not at all a issue if the airport is uh, having a SBAS station there. However, for the other users who want to use it on the ground, because the reference stations are relatively less, so in that case, as they go far away from the reference station, the accuracy will be reducing to some extent. Then we'll come to the Indian GAGAN system, that is a GPS aided geo augmentation navigation system. It has been developed with the cooperation effort between the India and the US. Raytheon company has established the GAGAN stations. It has costed about 770 crores rupees. The Director General of Civil Aviation has certified the GAGAN for en route operation, that is RNP 0.1, on December 30, 2013. So it is almost nearly a decade now from the time it has been certified. However, still the usage of GAGAN is very less in the aircraft industry, which should be increased actually. All the aircrafts should be equipped with the GAGAN enabled receivers. And subsequently on April 21, 2015, it has been approved for the Precision Approach Service also, APV1. And the signals for APV1 are available from 19th May 2015. Now this GAGAN system is the first SBAS system which is available in the equatorial region and providing its services since 2013. This provides accurate coordinate system, relieving the problem of getting accurate position. Now this improves the air traffic and other civil navigation, which results in fuel efficient air corridors. So as we have discussed in the previous slide, the benefits of VAS, same benefits we will have from the GAGAN. So we should increase the usage of it by using it on our aircrafts. So this figure shows the different location of reference stations across India. Now these reference stations enable the landing and takeoff of the aircrafts, and the nearest station we are operating the aircraft, that reference should be considered. This figure again shows that we have a master control station, and we have the Indian reference stations and the uplink station, which send the corrections to the geostationary satellites GSAT-8, GSAT-10, and the third one is the GSAT-15, which is an in-orbit spare for the application of the GAGAN. So we have benefits uh, of direct flying. Instead of a zigzag route, opted for the origin to the destination to be connected with the DMEs and the VORs. We can have a direct flight. So that will save time, fuel, and more predictability of the schedules. So that advantage we have with the Gagan. And sometimes some accidents are happening in the aircraft industry because of the overshooting of the aircraft. So I remember in the past decade or so, around two such accidents has happened. So if we are using Gagan kind of services, we will be able to use better uh, optimal usage of the runway can be done, and such kind of accidents where loss of life and material, that is aircraft, can be totally avoided actually through a optimal use of the airstrip. So these are highly recommended uh, for the aircraft industry. Of course the others can also use. Now we have a Gagan based ionospheric correction model also. There is a study by satellite based augmentation system, a novel and cost effective tool for ionospheric and space weather studies by uh, Sunda and Sridharan. This publication is there, and we can have our own ionospheric model along with the usage of it for the total electron content measure for the Indian region. So various researchers are using it for the various studies. TAC is also used for the prediction of the earthquake. It is in the research mode only. However, TAC is very important input to find the anomalies in the atmosphere. This shows the GSAT 10 position with respect to the course station located in Dehradun. So this is from our Trimble Pivot software, our GUI. It is, these screenshots are taken from that for the GSAT 8 and GSAT 10. So yellow dot is representing the course location in the IIRS campus in Dehradun, and the red dots are representing the GSAT 8 and GSAT 10. Thereafter, there is a recent publication which I would like to refer. I have not made a slide from that, but there is a recent publication, 2 decades of land subsidence in Calcutta, India, revealed by SAR interferometry and GPS measurements. So GPS is a very good technique to study land deformation also. Implications for groundwater management and seismic hazard assessment. This is by Shastri et al., a very recent publication of 2023. So here also I would like to refer here that in this study they have used the NVSat, ALOS, Sentinel data sets along with the GPS time series data which they have got from the Gagan station installed at the Kolkata airport. So these Gagan stations are also becoming a repository of the continuous observation of GPS time series data, and these are helpful in the studies on the land deformation as well. So this is one another usage which has come up recently, and they have done it for the area of Calcutta, where this is the Dum Dum airport which is placed here, and here is the Gagan station is, or the reference station is available here. So maybe some of you who are into this area, you can refer to this publication also, wherein they have come up with a successful study based on the GPS time series data acquired from the Gagan station. Thereafter, we will come to the EGNOS, that is for the European region. So that is also a multi-stage system. Currently, they are working with the GPS based corrections, and then they have EGNOS 2 also, which will take the corrections from the GPS, GLONASS, as well as the Galileo, because Galileo is also partly working right now. So they also do have the reference stations on the ground. with a master control facility where we will do the computations, and the correction parameters are sent to the geostationary satellite, and then again the geostationary satellite act as a repeated broadcaster for the correction parameters for the user. So you can see here this user, wherever you have the EGNOS enabled receiver, so it can be used by some vehicles over the road or the train or in some vehicle vessel in the ocean or the aircraft. So anybody who is using the EGNOS enabled receiver, they can use this for the correction. So Eurocontrol is a European organization which is taking care of the safety of air navigation. So ICAO, International Civil Aviation Organization, is taking care for the entire globe. Eurocontrol is taken care for the European region, and all are working together because ICAO is the main body which do so, and Eurocontrol is a civil and military organization which currently numbers 38 member states or 38 member countries, and they ensure the safety in the development of seamless pan-European air traffic management system to cope with capacity needs and environmental aspects. And there is a service called EGNOS Data Access Service, which offers ground-based access to EGNOS data through the internet, that is the SysNet protocol, on a controlled access basis, and disseminates differential corrections. See, as I told you, in the background in all the systems we are getting the differential corrections. So that means we have some correction. We have already known values for the base stations. We are deriving the real-time coordinates for the base station using the broadcast ephemeris data, then computing the errors using the known values and converting it into the correction parameters for the rover, that is the receiver which is being used at another location. So EGNOS ranging and integrity monitoring stations. So 40 stations are being used for them, 2 mission control stations, 6 navigation land earth stations, and the EGNOS wide area network. So all these combinedly again are providing a system wherein we have a ground based receiver, and okay, this was for the VAS system where they have about, currently they have 1239 airports which are working without the landing service. Should check actually, because you will get more confidence after going through the real time systems, because these websites are being updated and they have a lot of options. Even the job vacancies are also available here, various type of projects, announcements of opportunities, they are also available on these official websites. So here in the ground segment they are telling about what I have just now explained to you. They have 40 ranging integrity monitoring stations, 2 mission control stations, and so on for the EGNOS. So that's the figure which is used, and it has been updated till the April 2023. So you should visit all these websites which are being utilized and talked about in the entire series of GNSS course. Then thereafter we have the quasi-zenith satellite system, which is working as a regional navigation system as well as a satellite-based augmentation system for the Japanese region. So the basic system consists of 4 satellites, the QZSS 1, 2, 3, 4, and they have another 5th one working right now in the operations. So they are also working in a similar fashion as the IIRS. They have master control station. They are also using the empty satellites Himwari 6 and Himwari 7. So 6 has been decommissioned, so their correction signals are coming from the Himwari 7, that is the empty set 2 satellite. So they call their augmentation system as the MSAS, multifunctional satellite augmentation system. Again, it is working basically as per the computations of the DGPS, differential GPS, and they are able to provide 1.5 meter to 2 meter accurate horizontal and vertical accuracy signals to the users. So this is the design they are using, and you can see that this is one of the sky plots. Large number of satellites are there, and we have region Japan, city Tokyo. So these kind of competitions are shown in some kind of a GUI, and these are the two master control stations, Hitachi Ota and the Kobe MCS. So these are the two master control stations. Then ground monitoring stations are there, and they are using the empty satellite for the transmission of the correction parameters to the users. This is another figure explaining the distribution of the area control center, master control station, navigation ground earth station, central processing facility, network communication system, monitoring and ranging system, then the ground monitoring stations which are involved in the AMSAS, the Japanese system. And now similarly they are planning to move ahead with the system upgradation for the satellites using the 7 satellites actually. So they are also going for a design like in case of ISRO, we are moving from 7 satellite based system to 11 satellite based systems, wherein 4 spares will be there. Similarly, in case of the QZSS also, we will see that we have more number of satellites which are being coming in for the usage. So these slides I will be providing to you, and you can see the links also. So currently we have QZS0203. So this is live. I am showing you from the website, the official website from Japan for the quasi-Zenith satellite system as per 26 September 2023. That is the last update on the website. So they have QZS02, 03, 04, 1R and 01. These are the operational links, which are operational satellites which are being used under the QZSS. So 5 are operational. So 2 more they are going to add. And how they are adding basically they are using again quasi geostationary satellite system similar to the inclined geostationary orbit. So IGSO kind of orbit they are going to use. What I wanted to show you is let me just check it out 1 minute. Yeah, so 3 additional satellites what they are going to put is in the quasi geostationary orbit and the geostationary orbit. So they are bit different from the 4 satellites which they have planned. So they have a maybe it is given on some another website, but they have given the details of the 3 additional satellites also. So QZSS will also have 7 satellites. Now coming to the Russian system, that is the system of differential correction and monitoring. They are also providing the correction parameters based on the integrated use of GPS and GLONASS using their own reference stations, and they are providing it through a GSM broadcast from a SysNet server and the Antrip server. So they are also providing solutions which are based on the internet as well as the SIM card, that is the GSM based solution. So minimum in the GLONASS we require 18 satellites, whereas in the full operational capability 24 satellites. So they are also providing good accuracy. You can see that 1 to 1.5 meters in the horizontal and 2 to 3 meters in the vertical. That is how they are moving ahead, and they are planning for much more accurate in the future. So they are also looking for centimeter level positioning service for users at a range of 200 km from the reference stations. So that is the kind of aim they are taking care for the SDCM. So they are also using the geostationary satellite LUSH 5V, 5P, 5A. So these all details are also available and can be seen in detail. Similarly, coming to the Chinese system, Beidou, So Beidou, as we have discussed in the initial lecture, it is a scaled up system where they have developed Beidou first by providing service into the Chinese region around 2010. Then they upgraded it to Beidou 2 with the addition of the satellites with the improved footprint for the South Asian region. And then Beidou 3, few more satellites they added, and it became the global navigation satellite system covering the entire globe. So Beidou 1, Beidou 2 and Beidou 3. So Beidou 3 is nothing but the current Beidou. So no need of 1 to 3 now to talk about differently, but that is the way they have moved through a scaling procedure. So this is also used for the providing the standalone service from Beidou, differential GPS service, differential GNSS service from the Beidou, as well as the satellite based augmentation service also based on the Beidou. So all the kind of services they are providing using the Beidou. So in that they are using the GPS L1CA code also along with the Beidou GEO satellites. So because Beidou is using 7 different orbits, some are in the medium Earth orbits, and some are in the geostationary orbits, some are in the inclined geostationary orbits. So this system is acting as a multi-purpose system which is providing accurate system. And the satellite based navigation system, they have differential augmentation services since 2012, okay, for the Chinese region. Thereafter they completed the global system also in 2019, and they added another few spares in 2020, thereby completing the Beidou constellation also. So these are also available from their respective Chinese and the Russian websites. They are depicting the number of satellites in operation, what date they are going to moved out of service, what are the satellites which are going to be inducted into the service. So all those kind of details will be available in this. Now the next one is the SBAS system for the South Central America and the Caribbean islands, that is called the SCCSA. The pronunciation is a bit difficult because of the different language here. Now this is a project founded by the ICAO, International Civil Aviation Organization, with the participant and member states of the project, which includes the Argentina, Bolivia, Colombia, Costa Rica, Guatemala, Panama, Spain, Venezuela, and Sicily. Okay. So like that, if we see this final diagram, almost all parts of the globe, including the Australia also, they also have a system for that. We have a usage of differential GPS, satellite based augmentation system also everywhere for the benefit of the users. Now these are the various services which are providing the correction parameters to the users through some licensing procedures also. Some of the very well known among them are the TomTom telematics, which is being used by the iPhones. So all iPhone owners, they have this by default along with the background in image. So when I have used it, it will give you a better than a meter accuracy. So it's a very good. You have an image and you can see live your position on your phone. Then Trimble Navigation is providing the RTX service we have discussed in the previous lecture. Leica is providing the SmartLink service. Then we have other providers like Starfire, Starfix, OmniStar. So based on the payment, these various companies also provide the correction parameters. So Starfire is providing an accuracy of the order of 4.5 centimeter over a period of 24 hours of observation, whereas Starfix is providing PNT service using more than 50 reference ground stations with delivered accuracy of 10 centimeter in horizontal and 20 centimeter in vertical. So these can be used by various users. Their links are also provided in the slide.